Okay, we've been having lots of fun with optimization. And we're down to basically the last one I'm going to do an example of here. And this one is maybe not as applied in a situation, but it still can be, and it's an interesting little problem. And so we're going to take a look at it. What's the maximum area of a rectangle? So it's kind of like the corral problem, right? But that is inscribed in a right triangle with legs of 5 inches and 8 inches, assuming the sides of the rectangle are parallel to the legs of the triangle. So here's my right triangle, and here's the length. 5 is the height from here to here, and 8 is the length from here to here, right, of the triangle. And what we mean by inscribed, so this rectangle here, I've used the little dashed line for it. Of course, this is a 90-degree angle. The rectangle and the triangle share that angle. But then here's the rectangle, and there's this corner, upper left-hand corner of the rectangle is always on that point. So I can slide this point, to different locations. Like if I slide it all the way up to here, for instance, then I can have a rectangle that looks more like this. Okay. And I can slide that point back and forth, and you can see how the rectangles will change from being, very small height and longer length to shorter length, right, and bigger, taller, right. And so of all those possible rectangles that I can inscribe, which one, what dimensions, or what is the maximum area of such a rectangle, right? So here we're actually looking for what is the maximum area. And somebody says, oh, well, just a square, if it's a square. Okay, well, it turns out in this case that's not the answer. Okay, so what I'm going to do to make life simple for us in this is I'm going to imagine that this right here is the origin of my coordinate system. So my x-axis is going to coincide with the bottom of this triangle here, and here's my x-axis. And then going up this way, to use my ruler, is my y-axis. Okay. Now, what I'm trying to do then is find the area of this rectangle. Let me sort of shade that in here. I want to find the area of an arbitrary rectangle. Right? It's this area of this arbitrary rectangle. Okay. Well, this point, what are the coordinates of this point? What are the xy coordinates of this point? Well, what I'm going to do is I'm going to let this distance just be arbitrary, right? So let's just call it x, right? That's x is going to vary from anywhere from 0 if the point's right here, all the way to what? To 8, right? So here's x equal 8. And so the coordinates of this point, let's just call it x comma y. Let's just call it x comma y, right? So that length is x, and this, right, which is basically the height of our rectangle, isn't it? That's the y value, right? So that point has coordinates x comma y. This is x, and this is y. Okay? And so if A equals the area of the rectangle, then what is the area of our rectangle? Well, the height is y, but what's the length here? What's this going to be? Keep in mind that this 8 inches, right, is the base of this triangle. All the way here to here is 8. This is x, though, so what's this have to be? This has to be 8 take away x, right? 8 take away x is what we have left over. So x plus 8 minus x is 8. And so the area is y times 8 minus x. Right? The height times the base. The base times height doesn't matter the way we multiply them in. There it is. There's my area. Right? So if I know the xy coordinates of that point, I can indeed plug in and find the area of the corresponding rectangles. Everybody hopefully good with that. Now, what do we have? We have a function of two variables. We would like this to be a function of one variable. So how do I do that? Well, the way I'm going to do that, you could use similar shapes, but I'm just going to, the way I've got this set up, I want to take a look. My point has to be on this, the hypotenuse, if you will, of this right triangle. The point has to be somewhere along here, right? But that's a line. There's a line that coincides with that, right? What's the equation of this line? What's the equation of this line? The equation of this line is what? Y equals mx plus b. B is the y-intercept. What's the y-intercept for this line? It goes right through the origin. Y-intercept b is 0. So it's just y equals mx. What's the slope of this line? What's the slope of this line? What's the rise over the run? Going from this point to this point, where do we go? We go up 5 points, and we go a run of 8, right? We go vertically up 5, horizontally over 8, right? And so quite simply, the equation of the line is y is equal to slope 5/8 x. Now, the line extends forever in both directions, but we only want the portion that coincides with our triangle, the hypotenuse of the triangle. What does x vary from there? X equals 0 there to what? X equals 8. And I am going to include, could you include x equals 0 and include x equals 8? Yes. Now, if x equals 0, we're right there at that point, then y is 0. And we have no rectangle, technically. Okay? But we could say that the area of that rectangle is 0. Okay? I'm going to do it that way. That way I have endpoints, right? And we can use the technique where we can check the area at the endpoints and the critical points. Of course, if I let x be 8, right, again, then obviously 8 minus 8 is 0. The base goes to 0, right? Again, we have just a line. We don't have a rectangle. But again, I'm going to include that case as a 0 area rectangle. Those are the two extremes. So obviously we know somewhere in between, right, putting the point somewhere in between here is going to maximize the area of the rectangle that's inscribed in this triangle. So I'm going to take this value of y, and I'm going to plug it in here. Y is 5/8 x. Okay. And let's go ahead and multiply this through. I get 5/8 times 8 is 5x minus 5/8 x times x, 5/8 x squared. Well, this is actually now very simple. This is a graph of what? A parabola, right? So I mean, we could use pre-calculus techniques to do it, but we're going to use calculus. So I have the function on a closed interval. What's the maximum value of this function? So what are we going to do? Check the value of this function at the endpoints and at the critical points. So what is our derivative as a function of x? What's the derivative of this? Very easy, 5. And then I bring the 2 down. 2 divided by 8 is 1/4, so I get minus 5/4 x to the first power. And very easy, the derivative is 0 when basically 5/4 x is equal to 5, right? If 5/4 x equals 5, this difference is 0, or when x is equal to what? 4. 5/4 of 4 is 5. So when x is 4, that's a critical point, right? That's a critical point. And so what I'm going to do is I'm simply going to check the value of the function a at the endpoints and at the critical point. We already know the answer here, right? We said the area was 0, so this has to be the location of the maximum. If I plug in 4 into my original area function right up here, right? If x is 4, what do we get? 5 times 4 minus 5/8 times 4 squared, or 16. I get 20. Here I get 16 divided by 8 is 2. 2 times 5 is 10. 20 minus 10. I get 10. Right? course, my units are what? This is area, inches, what, squared, square inches, right? And this is the maximum area. Okay, now notice again, this was what we were asked to find, and this is the proof, right? Using it this way. Now, if you could have, if you had said instead, let's not include 0 and 8, let's have an open interval, that's fine. You can do a sign check on the derivative, and you would find that local maximum at 4. But again, if we can include endpoints, it's much easier, and in this case, I can go ahead and do that. Let's just go ahead and give the dimensions. That wasn't part of the question. We know this occurs when x was 4. So if x is 4, what's the y value? Remember, the relationship between x and y is up here on this line, right? If x is 4, y is 5/8 of 4. Which is 2.5. And so the max area is when x is 4 inches and y is 2.5 inches. So I just want you to note that's not a square, right? So it's not a square that maximizes. So it's a little bit different in this case because of the fact that we have to have, wait, I'm completely wrong, excuse me. The max area when x is 4 and y is 2.5. This is not the dimensions of the rectangle. Let's go back to the rectangle. I almost messed up. The rectangle is what? Right? Height was y, yeah, but the length was what? 8 minus x. So the height, so rectangle height, max area when what? Rectangle height, which is equal to y, is 2.5 inches, and rectangle, we'll say width, is 8 minus x. We'll be okay though, because what's 8 minus 4? It's still 4 inches. So, so actually it is a 2.5 by 4 inch rectangle. But again, not a square. Okay, so an interesting little problem. There are some others like that, and a lot of times these problems are set up to where, you know, we have some constraints. If I didn't have the constraint to say, you know, you don't have to be inscribed in this rectangle, I can make the not be inscribed in this triangle. This rectangle can be as big as I possibly want it to be. Okay, so I'm sure there's a lot more questions. I'm going to include in my completed notes the solutions to a couple of other problems, one from the textbook and one from my non-textbook homework. But you really want to try these problems. There's a lot of variety. They're kind of like related rates in the sense, you know, you've got to figure out, assign variables and get your function in this case. Sort of like you were getting the equation relating the variables in related rates. You know, and then you have to decide, do I have a closed interval with including endpoints, or is the interval open and or unbounded? And then, you know, I use different techniques for finding the max or min. Okay, so this is it. This is it for the semester. You can now crack open the bottle of sparkling grape juice and celebrate. Oh, but not yet. You've got to finish the homework and prepare for our last test.